Hello. All right, we are doing an experiment, as we always do. I called it educational series, which means we will be talking about something that is somewhat more standard, somewhat more conventional. And I have a personal disclaimer to make, if you actually. So we're going to cover a relatively popular question. I'm doing my best to make sure that the kind of stuff we discuss here is not really meant to help you pass the interviews better, but rather to help you understand how the systems work in depth. At the same time, I'm fully aware that quite possibly you have found this video because you would like to prepare for an interview, and I think it's fine. I think we should do our best too. As long as some of you can find more joy in understanding things deeper, I think we've done our job well. This was the first half of the disclaimer. The second half is that I'm going to call this episode TinyURL because I use TinyURL, but it's a proprietary company name. The canonical name for the problem is URL shortener. Everything else, such as Bitly or TinyURL or whatnot, are respective company names. So hope they are fine with me giving them some free PR. What we will do today is we'll try to approach the problem both as in how would you do it from scratch and how you are expected to talk about this. We'll try to build it from the most common standard available building blocks. We'll try to learn how to better reason about how these blocks connect well and how to not try to connect them. And TinyURL is kind of a simple problem, more or less, but I do want to make a note that knowing how to solve this problem actually opens doors to quite a few other bigger problems. As always, feel free to interrupt me at any time. I'm totally cool with that. When we start talking about problems of this capacity, of this magnitude, I should say, there's a thing called functional requirements. I never like this section per se, but it's important to outline some requirements just so that we know what we're talking about. The trick that helped me internalize the idea that this is a good starting point, is the understanding that most people have different defaults. Most people make tons of assumptions, and oftentimes these assumptions don't really align well with across the boundary between two people. So outlining carefully what do you mean by X is oftentimes a good idea, and the skill of being able to outline this in just one sentence or 1 minute is a huge skill. So speaking of functional requirements for the TinyURL problem, for the URL shortener, here would be a couple of questions that I think should be asked. Can you change the destination of the shortened URL? So can I have a long URL, shorten it to something, and then change this something to a different long URL if I'm the owner of the short URL? It's a good question, and I think the answer should be yes. Are there constraints on who can create the URLs? This has to do with login and authentication authorization, huge topics. Let's ignore them for now. Let's say we don't have any Auth, or more like we do have the Auth that is taken care of by some other team, and we just use it. For example, you can log in with Google, and that's good enough. Do short URLs expire? As in, if I create a short URL and nobody has clicked it in a year, should it still be there? Still it should be there, at least for now. For the purposes of designing the system, it's a good constraint to require it to be there. Can you choose your own short URLs, vanity URLs? I think fundamentally we should allow this. Do we design for the cloud, or is it our own hardware? I think we should do both, and I'll talk about the differences later on. And now the dreaded question about scale. How many URLs do we have, and how many clicks do we expect to render? Well, if you're discussing this in an interview setting, answering this question is part of the interview. So the interviewer would say, well, you tell me if it's a world scale service. So let's go there. There used to be the times where they would ask you why a manhole covers round. Thankfully, those times are gone, but we do talk about real life numbers. I have to confess, when I tried to estimate these numbers myself, I made a mistake by an order of magnitude or slightly less. So I looked up these numbers. If you think 1 URL per human on the planet is too much, Bitly alone is at least 5x that. In Wikipedia, it says that Bitly has shortened 37 billion URLs by 2018. So basically, yes, more than one URL per human being on the planet is to be shortened. We'll talk, I'll cover briefly how can this be possible later on. Now, for this, for read access, for QPS, I was thinking of 1 billion clicks per week being sufficient. In reality, it's 6 billion clicks per month, so that should be fine. If you divide the numbers, if you do the math, it would be 2.5 thousand queries per second on average. And when you design a system like this, you should know that average is not the peak, because there are day-night cycles, and there are peak times that are of higher load and then lower, then higher again. So the good heuristic is to assume you have 2.5x average to get the peak. Could be slightly more. Thanks, Antonio, for this link. Wikipedia has its internal numbers published. They have this wonderful dashboard on Grafana and Kafka, which you can click. This link is not to Wikipedia. This link is to its own internal tracking service. If you look at the orange line, you can see the daily cycles, and it's approximately 2.5x. It's slightly under 20k at lowest times, and sometimes slightly over 60k at peak load. So yeah, 2.5x, 3x. I'm not saying it's always 2.5x, for the record. If you have a Switzerland-only service, let's say if you have Swiss-German-only service, you would hardly have any load when the German part of Switzerland is asleep. But then you would have lower absolute numbers. So the moment you get to talk world scale, you probably get to this approximately 2.5x coefficient. In reality, it doesn't really matter what do you say there. You can use 2 or 3 or 5. As long as you know this, that's good enough. For the record, my style is to generally ignore the slides. The text. The text is here for you guys to be able to retell this to those who have not seen it before. So I'm going to just go with the flow. I'm not going to read everything carefully. Now, there was a question, the potential question, can the URLs change? On the one hand, from the computer science perspective, it is a lot easier to build the system where whatever is added never changes. It honestly is. It is substantially easier. However, this actually requires a guarantee that there's an external guarantor, an external entity that makes sure that whatever was added would not change, which is clearly not the case for TinyURL, because an example I would use here a lot of times, what if the same URL is being created or changed simultaneously by a user from Australia and from the UK? You would have some system that would need to figure out who was the first, who made this change. And if you can guarantee this never happens, well, yes, you can build an immutable system. For example, if every single TinyURL is assigned at random, you can just say, you know what, every single location, every single server has its own set of range of short URLs to use. That's fine. But in practice, at some point, some people would need to change the URL, and whether we like it or not, for any system like this, business requirements come first. So at some point, you would need to enable some users to change the URLs, and you're back to the fully mutable system. Authentication, as in login, I do want to point out, and I think it should be pointed out if it's a real question. If it's a real question, I do want to point out that supporting user login is a major problem. You need to keep the data safe, both from loss and from leaks. You need to keep the data in the right jurisdictions, which are getting harder and harder to manage every day, well, every year. You need to validate emails or phone numbers, which is a special service, and actually it's oftentimes a paid service. Sending text messages to phone numbers is not free. And somebody could try to abuse it to make sure you pay lots of money and go bankrupt. The world is cruel sometimes. And at some point, you would need to tie payment methods to users, which by itself requires some concept of the user, right? And also, I should mention that there's a problem of rate limiting and DDoS protection, which can happen both at the mutation time, but it would happen far more frequently at the URL resolution time. Simply put, if every single time somebody's trying to go to a short URL that doesn't exist, if every single time it happens you go to the database, there's a good chance that someone would bring the whole system down, because the number of queries per second they can issue is huge. And if you go to a database every single time, you would either your database will be super expensive or you will bring it down. So there are solutions to work around this. come into them in a few minutes. An extremely important question from my point of view when it comes to system design. I'm kind of biased in my own ways. I think system design is mostly about balancing on the constraint of the cap theorem, of this eventual consistency of exactly one's delivery. So that's what I think true system design is about. If it can be designed as in design the API, design the database schema, and you're done, that's not true system design to me. Don't get me wrong. I'm not saying these are easy problems. It's just I want to take it like a top-down approach. So to me, this is the most important part. Which guarantees do you have to provide? When a system is up and running, you have enough capacity, nobody's attacking you, no machines are dying. Well, even in these ideal circumstances, you still have some trade-offs to make. Clearly, you want to maintain high availability and serve all the requests, but you always have this latency throughput trade-off and latency consistency trade-off. Latency consistency is, what if I'm changing the URL? Or what if the URL did not exist? I just created it and I sent it to you by the messenger. And you click on the same link. So T0, I create a short URL, T0 plus half a second, I send you the link in a messenger, and I'm in the UK. In Australia, T plus 1 second, you click it. What if your system, well, what if the system tells you this URL doesn't exist? You refresh the page and it's there. Well, that's on the one hand, it's perfectly fine. It's not too bad that the URL takes a second or two to propagate. On the other hand, it's part of the requirements by the business. You could say that maybe 1 second is acceptable, 3 seconds are not acceptable, and this is exactly this latency consistency trade-off. Or you could say URL creation would take slightly longer, but then or maybe I need more machines to serve this. But I'm giving you the guarantee that in 99.9% of cases, it will take under a second to update all the caches everywhere, so that from anywhere in the world, this URL is going to be active or disabled if you just removed it for some legal reasons. The latency throughput trade-off is for the same number of machines, for the same amount of CPU you can use, or CPU and RAM you can use. You can serve more throughput, more queries per second with higher latency, responding to some of those slower, or you can have strict SLAs, strict guarantees on the response time, but your peak throughput would suffer. We don't have to talk about this right now. It's just important to know that it's the extreme case of fine-tuning the parameters of the system in an outage or near outage situation. If something goes wrong, and at some point something will go wrong, at least if you design a system, you have to assume at some point things will go wrong. Well, the number one consideration would almost always be don't lose the data. This means that on the one hand, your databases should be replicated, and number two, you have backups, but they're not sharding your backups, so that you would never know if the backup is valid or not until you try to apply it. Once you have backups, you need to also to make sure you have mechanisms that apply those backups, and you should check those mechanisms frequently. And then if the system is somewhat under heavy load or is otherwise breaking because some machines are down, some network connections are down, you need to decide between availability and consistency. There's a cap theorem. We will not go into this today. It's a different conversation. There's a PAC, and then there's a cap theorem, and then it was extended into what is called PAELC theorem. CAP loosely stands for CAP stands for consistency, availability, partition, tolerance. What it tells you is that you cannot have all three. If you want to have partition tolerance, which is your system keeps operating, if it's broken into pieces that don't talk to each other, if you have P, then you can have either C or A. It's either available or consistent. If you have C, you can have either P or A. If you have A, you can have either C or P. And this PAELC says that if effectively you need to make a trade-off, which I was speaking about just a minute ago: latency throughput, latency consistency. In practice, in most real-life applications, you would go with eventual consistency, which means, hey, if something is broken on our end and we're working to fix it, the system kind of serves the requests, but some data could be stale. So maybe on average, your new URL is available after, let's say, half a second or 1 second. If it's under heavy load, it could take up to an hour to get there. That's not the worst case scenario. I mean, Slack was down for quite a bit just yesterday, so things happen. Another important point to make is, even if what we're doing is solving TinyURL, there are tons of things we have to do besides URL shortening. we outlined the login part. And I have to briefly mention that, yes, if you need to remove the URL somehow or revoke access from somebody who's a bad actor, you may need to have this done very quickly, literally within seconds. And if that's your constraint, fulfilling this constraint alone is likely harder than solving the whole TinyURL problem. It's just one of the differences between theory and practice, between real-life architecture and interview-style architecture. So I'll just briefly outline a couple of things you may need to do if you're doing URL shortener. Number one, I think, is statistics. Clearly, after the users can use your system to shorten the URLs, they would want to look back and see how many times did other people click on my URLs. Show me top 3. Show me the top gainers of the last week. That's only natural. That's one of the major use cases for URL shortener, besides actually shortening the URLs. In the modern world, you would absolutely need to be able to render previews for those URLs. So if you're going to send your short URL in a messenger or publish it on Facebook or Twitter, most platforms would offer some preview, some snippet, maybe a picture, maybe some text snippet. You may want to crawl the page yourself, first to make sure that the page is active. You probably should let users to create short links to pages that are currently inactive. But you may want to crawl the page yourself and maybe recrawl it eventually with some frequency so that you don't load the page too much when people are trying to send links to that. It's a detour, but it's a big detour. It's an example of some other things you didn't think about right away, but you have to work on that. Billing, another huge feature. Most likely your business will be making money somehow, maybe with some expanded analytics or whatnot. So making sure people do pay for the services they use. It's kind of part of authentication and authorization, stands in between this and the actual URL shortening. Just pointing this out that it's another potentially huge problem. Anti-fraud, audit internal tools, customer support requires tons of mechanisms. It's ironically easier to build a URL shortener which can quickly resolve short URLs into their destinations. But then you say, hey, you know what? This domain is a pretty bad domain. I need to blacklist it. I need to make sure I need to blocklist it. I guess that's the modern term. I need to make sure we never direct users to those domain names. Well, if your database is if your key value store is sharded by short URL, looking through all the URLs and finding the ones that match that domain or the domain pattern, surprisingly, is a hard problem. It's not too hard, but it's something to think about in your data schema design and whatnot. Regulatory compliance, sometimes you have to store the data in some locations, which is hard in terms of design. It's hard to add this support if you didn't think of it right away. It's not hard to design for it, it's hard to add it later. Sometimes you have this right to be forgotten in some jurisdictions, such as Europe. Also pretty hard to support because deleting data is non-trivial. You can delete it from your database, but how do you know it's not in the cache? How do you know it's not in the Nginx logs or whatnot, in your cloud provider logs? Potentially tricky. Of course, backup and restore. I mentioned that you need to make sure you can restore from backups. So the point here is that even if what you need to design is the URL shortener component, tons of things are hidden in the plain sight. So I had to mention all this, but in the real life, again, I don't want to talk about interviews, but I have to. In the real life, just be aware of this. Don't talk for as long as I was just talking. Just make sure you can comfortably support any of those conversations and get to the real problem as soon as possible. Well, more like within the first 10-15 minutes. To the juicy stuff. This does come to a surprise. This does come as a surprise to quite a few people that I actually usually advise against talking about RESTful APIs. Not because I don't like REST, but because I found it out the hard way that people don't know what REST is. And that's especially true. So if you're just talking to me or to a friend of yours with whom you're designing the system, you may be calling the same thing REST. So it won't harm your conversation. If it's an interview or if you're talking to somebody outside your organization who knows what REST is, they would be quick to think that you don't know what REST is, and they would be right. Good interviewers would immediately take note. REST is not really, well, first of all, REST is state transfer. REST stands for representational state transfer. If it's remote procedure calls over HTTP and JSON, that's not REST. In fact, REST is not tied to the protocol at all. REST is about making sure you have resources with their canonical names, and you can access those resources using some standard means. It's supposed to be idempotent, so the same request made multiple times is by design guaranteed to give you the same result, unless you speak this on, and it's of course about hypermedia if you want to be properly RESTful. That's where Swagger comes into play. That's where self-describing APIs, self-describing schemas, and self-describing methods to change those data points. That's what REST is. In the case of URL shortening, on the one hand, I'll actually give you an example. I was just recently speaking with some people, and we were designing the API for a messenger. So we had a resource HTTP endpoint for the message room, like a chat between two or more people. And then, which is perfectly fine, right? You can get this resource /messages / chat room ID or whatnot, and you get the messages for this room in some order from some timestamp or whatnot. And then the question was, how do you add the message there? And the idea that you have some /messages / message chat ID /post message or /add message is just so unrestful, because REST by definition offers a post as an HTTP verb, as a method to post there. So you have the resource message board or a chat window within this ID, and you can post to this resource, or you can get it, you can head it, patch it, etc., etc. So if you think that you're having a RESTful API, but then you add an endpoint to mutate something that you already have the resource ID for, that's not REST. Don't do it. With this being said, there are good things about REST. One is that it handles authentication kind of natively. So if one of your clients, or if your major client is a web browser, chances are the user is logged in. Chances are their login credentials, well, not credentials, of course. Chances are their login authentication token is stored in the cookies. And with REST, you can always say, oh, I handle authentication via hooker headers. And that's all you need to say. If you have your own RPC-based API, you would need to make sure to not forget to put some authentication token in every single request. So with all this being said, for the URL shortening problem, even though I'm usually advocating against designing RESTful APIs, URL shortener shortens the URLs, and URLs are HTTP requests. So whether you like it or not, you would need to have some HTTP interface. So what I suggest as the bare minimum is the following. Let's only focus on the users who are clicking on shortened URLs. And we probably need to support two methods, get and head. And all you need is the shortened URL. That's it. Get just either redirects you to this URL. Traditionally, you would do it via standard HTTP 302 found. I'm not entirely sure it's the best way. I'm not a front-end developer. Maybe for some referrer protection policy or whatnot, you could do it differently. I'm not an expert. But for the bare minimum, logically, you can do HTTP 302 found and redirect to the destination URL, or 404 not found. Important point, if it's HTTP, if you get your request through an HTTP protocol via TCP connection, you don't need to ask for the user's IP address, you have it, which comes in handy because most likely in the statistics you would want to show where do the users come from. So if I create a short URL and it gets 100 clicks in the first day, you probably want to show me not just the number 100, but also that these people come from United States, Canada, UK, India, Australia, Russia, whatnot. So this is traditionally determined by the IP address. In addition to the GET request, I would also add the head request, which is just what you use to generate the preview, the thumbnail, maybe the fev icon, or whatnot. Whatever it takes to render the preview of this page without having to crawl the full page. So you do in social platforms, social media platforms, or messengers a big service if you can generate previews for them, so that they don't have to crawl the destination and then generate this preview. And you could say it's REST. In a way, you could say, oh, why don't you let me patch a certain URL to change it? Why don't you let me put a new destination there? It will be perfectly RESTful. I would rather not do it, but it's a valid conversation. What I would do instead, I would actually write the specs as if they are method calls. I'm deliberately method as in functions. I deliberately use some weird mixed language so that it doesn't look like any specific language. But what you need to have is the resolution, resolve, and the preview. They kind of are the two get and head that I suggested before. And for users who are authenticated, who can create new URLs, I would also add two more methods for the very bare minimum to shorten URL and to get the stats for a URL. To shorten the URL, I would need the auth token or auth data, more or less, full URL, and maybe optionally the desired short URL, desired vanity URL. And it's going to return me some typed object because you may succeed or not succeed. So you would return something that has true false as success, optional short URL if it's successful, and maybe some error if it's not successful. In practice, the error would not be a string because what would handle the response from this internal API call is your own frontend, which would probably be multi-language, internalized, etc. So it shouldn't be a string. It should be some string key, maybe some error message pattern and some fields to populate so that you can render this message in 100 languages. Again, I'm talking about the differences between simple design and real design. And for stats, again, super simply, I would like to make it possible that the user who has created a certain URL can look at the stats for this URL or multiple URLs. Again, these are by far not a complete list of all the getters. For example, if as a user I may want to get the clicks count for all my URLs for the past week sorted by number of clicks. Sounds simple, but for certain data access patterns, it would be an expensive call. So you probably would need to design the API so that it supports this kind of queries. In practice, if you have, let's say, 1,000 URLs shortened, or it's not hard to imagine an organization that shortens all its URLs under one account for marketing purposes. Not hard to imagine that they have tens of thousands of URLs shortened for different marketing campaigns or whatnot, different ads. In which case, the API to let you browse through those URLs would need to support some kind of pagination or sorting or filtering, which again is pretty hard, by the way. APIs with pagination are not easy, surprisingly. It looks simple, but it's not. Because what if I'm looking at the first 10, then I'm going to look at the next 10, but I'm doing skip the first 10, but then one of these first 10 was deleted, so now the 11th is the 10th, and I'm missing this when I'm skipping through. So you probably need to create a scan session, which is tied to certain version of this of the sorted list or whatnot. Painful, trust me. So yeah, I mentioned both of these. I mentioned many of these. Right. The whole point is that it would require more machines sometimes and even more code to run than the very URL shortening part. Spoiler alert, I actually believe if I were to design the URL shortener myself, just the part that shortens the URL, I would not need more than single handed number of fingers on my single hand. I mean, I would probably not need more than 5 machines at all to shorten billions of URLs because of the access patterns and stuff like that. It should be easy. And then I read Bitly has about 400 machines, likely more than 500 right now, which came as a surprise to me, to be honest. But then when I dug deeper into making the slides, I realized that, yeah, for all the statistical requests, for all these aggregations, for all the monitoring, for all the anti-DDoS, for the payments, it kind of makes sense. That's how the world is today, and it's healthy. Again, not saying it's impossible to do. Just keep in mind that when you're talking about URL shortening, you probably are talking about a very simple subset of the problem. That's where the difference between real life and theory is. Before we get to the actual design, what do we need to mention? By all means, do interrupt me. I feel like I'm the person talking, which I'm fine with. Just it's supposed to be a meetup. So general thoughts. Thought number 1, I'm going to have a very high skew towards reads. The system is going to be very read heavy. When I made this slide, I wrote it's going to be at least 1,000 to 1 read-write ratio. So at least 1,000 reads per 1 write. Then I've changed it into 100 plus. and I'll tell you why. The truth is that in the real world, all the distributions are exponential. So I'm almost positive that of the billions of URLs shortened, you can come up with the top 10,000, and they would be 99.9 something % of everything clicked today and tomorrow. That's normal. In this case, the read to write ratio on these URLs would be huge, could be 1,000,000 to 1 easily, and well, could even be more. And yes, most clicks access these URLs. But then the other end is also true. This distribution is usually a very heavy-tailed one. So I would argue that the median number of clicks per short URL is probably 1, if not 0. Because for one URL that is suddenly becoming super popular and it's advertised, it's published everywhere and stuff like that, for one URL like this, there are hundreds of short URLs which you have created, clicked yourself, maybe sent your friend, maybe posted somewhere where nobody clicks it, and that's it. So I wouldn't necessarily say that the read-to-write ratio could be as high as 1,000,000 to 1, even though in extreme cases it will be. Quite the contrary, I would say that most URLs are created once, clicked once or twice, or never clicked, but you still need to keep them somewhere. Thankfully not in memory, but on disk, absolutely, in some database, absolutely. So yeah, I still think the read-write ratio would be closer to 1,000 to 1 or more, but I wouldn't bet on it. May well be like 150 to 1.
Dima, you asked to interrupt. So for this one, actually, if you have a look at Twitter and how Twitter shortens URLs, basically any link that you post gets shortened just to get the statistics, if ever anyone clicks it. And most of the links get never clicked. So generally you have two different spikes of this distribution. It's not a normal distribution. So you have a lot of some links that are clicked very often, and most links are actually write only, like no one ever accesses them.
Yep. Well, it's never normal. It's more like a power law, or more likely Zipf's law. But yes, I don't think I quite agree that it's only shortened if it's clicked. I'm pretty positive that it's shortened right away, because when you hover your mouse.
Yeah, it's shortened right away, but so generally when you design such a system, you can delay a piece of work on actually propagating that into statistics or some kind of storage until it's clicked very first time.
That's a good point, and we will get there soon. As in, when do you need to? So this problem will all be about caching. It's on this slide, like 2 lines below. But basically, yes, you need to decide when to put the URL into the cache. And it's a good question whether you would rather put it into the cache right as it's created or as it's clicked first. I don't see the reason to not put it into the cache right away, because probably the user who created the URL would click it, and probably they would benefit from their friends not waiting until this URL is cached. And quite honestly, at least recently, used cache expiration would get rid of those extra cached URLs fairly quickly. But it's a good point that you don't have to, at least for statistics. Well, so we're not going to cover statistics today, but as a number of clicks and geo-distribution, what you would usually do is some aggregations per node, and then they are eventually consistent, as in, so let's say 10 machines collect stats for different URLs, and then every 1 minute or 50 minutes, they send the stats upwards. So chances are, if it's just one click, it may even not be noticed. No one really cares. I mean, I think it will be, because the users like to see 1, 2, 3. But yes, it would not be taking too much of RAM and CPU if it's just one click in the first 1 hour and that's it. Okay, so read heavy, we covered. Another huge point is that...
Dima, may I ask one question? And what about this topic in scope of UUIDs, for instance? So if it can be changed, okay, but if let's say use sort of UUID algorithm, then you can more or less rely that it's not changed, if I'm not mistaken.
Yes, if you have UUID style. So I guess by UUID you just mean a huge random number, random identifier that is, for all practical purposes, unique.
Yeah, but it consists from 8 parts, basically, more or less, 8 sequences. So,
well, it's just tons of entropy plus some seed that makes it
yes.
even more impossible for two UUIDs generated by different machines to be identical. So if you have, look, from my point of view, as I said before, system design at large scale is all about concurrency issues, exactly once, delivery, PubSubs, and whatnot. So if you always use UUIDs, then yes, you never change things. If you always use UUIDs, then you can always assume that if you would like to add some UUID plus URL tuple of 2 elements, even if you would add it twice because of some random issue of retransmission, your browser died or whatnot, or your backend service died and restarted. Even if you add it twice, you would add the same destination for the same UUID. If you build a system like this, you can cut a lot more corners. But then again, I would not recommend it because for any real-life system, at some point you would need to at least delete some URLs for legal reasons, for example. Even if your policy is and never delete stuff, at some point, if you design it as an append only, never delete, because that's what your company motto is, at some point they would tell you, hey, in Germany, either you support deletion of certain kinds of content or we ban you. And your CEO would tell you, hey, you know what, screw your purity. If you want to operate in Germany, let's do it this way.
Yeah, but wait a second. When we talk about the shortened URL, it means that it's kind of a redirect, right? So then you just turn off the redirect in this case.
Well, technically, you have to, from the user standpoint, what you when you say turn off, you either wipe this record from your database or have some second order database that says it's wiped.
Yeah, exactly, or invalidate. So
fine. Then what if you would like to revalidate the message? How many layers do you have?
Well, it depends.
So the moment you can think of a scenario where two people concurrently trying to create or change or delete the same key, and you need to handle this concurrency, at least to the degree that after all the back and forth is done, the system is in a consistent state. Everywhere across the globe gets the same result with the same shortened URL or UUID. The moment you have this consistency issue, you need to design the whole thing that potentially supports mutations, potentially supports change in the destinations. You're making a really good point. If you're building a torrent protocol where once some chunk was published to the network, it has certain hash, and whoever wants to get the data for this hash is guaranteed to get the same data or potentially not get any data. If you have this guarantee by design, you can do a lot better. In the real life, you would hardly have this luxury.
Okay.
It is a good question. I have at least 2 more slides touching on this, so stay tuned. So read heavy we covered. Another important thing is that URLs are entirely independent. Entirely as in not a single atomic mutation. I dare to say transaction because we don't have to use a SQL database, but not a single mutation of the state of your system would affect 2 URLs atomically. So both simultaneously or none of those, which is a perfect case to partition or shard your URLs by their keys. Of course, you would compute hashes of those URLs and shard by the hash, not by the URL. But it's important to note that they are entirely independent. And given they are entirely independent, and given we have a really read-heavy system, what we are designing internally is a large key value store. The key is the shortened URL, or UUID if you wish. The value is the destination. Once you have to design a large key value store, once you have to design a large document store with a huge read-to-write ratio, you should immediately realize that the problem is all about caching. If the same URL is the same key is accessed far more frequently to be read than to be written, the whole problem could be about caching. I mean, I would go as far as saying that all the shortened URLs can be stored on a single machine. And in fact, if your caching works correctly, if you only need to update caches somewhat infrequently, your single machine would have enough capacity to update all the caches. But all the reads of the frequent URLs should come from memory, and that's where caching comes into play. So it's the famous Pareto principle: 20% of people drink 80% of beer. In this case, it's really a lot more skewed. like 0.1% to 99.9%. It was my random wild guess. It could be even more skewed. So how to design caching is a whole separate conversation. Cache expiration policy or cache eviction policy is a big topic. The standard solution is to use what is called least recently used, LRU, caching policy, which is a very simple idea. Let's say you, computer science-wise, sometimes you would say, oh, I'm gonna keep 1 million URLs on cache. In practice, of course, you don't say 1 million URLs. You say, I'm gonna allocate a gigabyte for cache. In practice, you would allocate all your RAM for a cache because that's the most important thing you have to do. So let's say you have a 32 gigs RAM machine, and you say, I'm gonna allocate 29 of those or 30 of those for cache. You keep them in a doubly linked list, keep them in a hash table too. Every single time you access some key, it is an order of one operation. You remove it from the doubly linked list from where it is. You use a hash map to find this record in order of one from a hash map. You move this node to the head of this doubly linked list, which is also an order of one operation. And then you always maintain this single chain of keys so that you can always iterate through them from the least recently used to the most infrequently used, from the most recently used to the least frequently used. The point is, once you need to add a new key and you're out of RAM, you just go through this queue from the tail, and you look at the key that was accessed the furthest into the past. So you don't need to limit your cache by, let's say, I want to cache every single thing accessed in the past 24 hours. That's hard, and eventually you will either run out of memory or you would be underutilizing your memory. What you would do is you would say, I use this many gigabytes of RAM as a cache. I keep some hash maps, I keep some table, I keep the actual contents, and whenever I need to add the new key and I'm out of memory, until I have enough memory freed, I remove from the further end of the queue. And the actual difference in timestamps between head and tail would be your cache retainance. I wonder what that is. So you can measure this amount of time. So you would know that for this particular cache node, you cache the URL approximately for 17 hours or 170 hours. So that's another good metric to monitor. But fundamentally, all you need to do is to say, I'm going to cache everything in a least recently used fashion. So most frequently, if something is used more than once or twice, it will be used with some frequency. And I would guarantee that in practice, if the link is clicked at least, let's say, every 15 minutes, chances are, if you look at all the links clicked within the past 1 hour or 15 minutes, they would fit a single machine in memory. But that's just because I'm a high-performance optimizer for the system design. In an interview setting, you don't need to know all this. You can just say, I have a cache. I can distribute it, I can shard it, because I can have multiple machines for the cache. And I allocate as much RAM as I can. And I use the least recently used cache eviction policy to make sure that whatever is clicked frequently is guaranteed to stay in the cache. So given this is a solution we need to design, the meat of the problem, the true gist, is how to maintain this database or whatever is your source of truth, plus the cache, how to maintain them in sync. Because that's the infamously hard problem, and I'll tell you in a moment why. Finally, by slide 17, I wonder how much time did it take to get here. So finally, by slide 17, we have a diagram. I actually was tempted to draw a bunch of those with different designs, but then I realized it would be too hard. So let's just stick with one. I'm not saying this is the best design for production. That's an important point. And I'm not even saying that's the good design for production. But I do insist it's one of the best pictures you can draw if your goal is to demonstrate that you understand the problem, both if you're interviewing and if you need to prove to somebody that you know how things work. So there are actually not too many components here, so it's fairly easy to walk through all of those. So it's a single data center design. The outer dashed rectangle is a data center. I've deliberately made an assumption that I can separate the users who just get the URLs, which means the users who just visit the pages, from the users who create new short URLs. In fact, in my design, I have different load balancers, read-only and read-write. It's not a requirement. By no means you have to do it this way. I think it's a very good practice for a very simple reason. When your system is down, chances are you would first want to fix the read-only part, and then you would fix the read-write part. So if you don't separate them and you're being attacked because it's a DDoS, or if you don't separate them and something is broken on your side, you would have to fix everything to enable even the basic functionality. Even though in practice, when your system is down, you would much prefer to say, you know what, you can create new URLs. I've lost some 1 hour of updates. I'm going to apply those later. But at least whatever was created more than an hour ago in the past many years, the users can click those URLs with no problems. That's just my preference. Again, by no means I'm saying it's the best design. I just think it's a simple enough thing to mention. So then the read-write requests would go to application servers, app servers here. They are sharded, or multiple of those. And in my design, they talk to some single database, which is a source of truth. I'm not saying it's a single machine database, no way. And I'm not saying that the database cannot be distributed. It's just for the simple design, I would say, hey, because my design is fundamentally cache-centric, so it's read-centric, not write-centric, the load on the database is fairly low. If we do the math carefully, and I've done it, you would probably update a couple hundred URLs per second, even for the world scale thing, even for the numbers we outlined before from Bitly. So any single database on this planet can handle 500 updates per second. It's really hard to build a database that cannot handle this. So you can use any database that you trust, as long as you can shard it in different locations and make sure that if one server dies, the other one picks up. And you can logically assume it's a single database as a source of truth. Then my application servers would be the entities that update this database. Again, it's really hard to write an application server that cannot handle 300 queries per second. I think 300 was the number I got in my math. So let's say 500. So technically, it doesn't have to be multiple machines. But again, it's a good practice to have more than one, at least two, the leader and the hot standby. Just in case the machine is dead, things do happen, your system is still up and running. The cache server would have a lot more servers because it has a lot higher load. As we figured out, the read-to-write ratio is huge. So if you may be able to live with 2 application servers or 3 application servers, you'll probably need at least a few dozen cache servers. Again, I'm the high-performance guy. I'm a C++ guy. I would argue take a 64-cores machine that is kind of expensive, but not too expensive, and I'll serve 100K requests per second from this one machine, all in memory, all on the cache. If it's not a memory, it's in a local 1 terabyte disk, and least recently used cache on disk plus memory does miracles. I would not recommend you talk about this unless you know what you're doing. In practice, you would do better by explaining that, oh, this needs to be sharded, you need multiple servers. If some of those die, some others can pick up. And you can then talk about the actual hard part of the problem, which is how to keep these guys synchronized. And the standard solution is you have a PubSub bus, most likely Kafka these days, although I would not be opposed to other solutions. Again, we'll talk about this in a moment. What will happen is, once you need to update something, this person in the sunglasses would send a request to the load balancer, goes to an app server. The app server would have to simultaneously, which is impossible, but bear with me, simultaneously update the database and put this record that it was updated into the PubSub. You might want to put this record as in just this key was updated, so the cache server would have to go to the database along this dotted line, dashed line, to actually get the value for this key, the destination. Or you might put the whole cortege, the whole shortened URL plus the value, so that the cache server doesn't even have to go to the database to update its own cache. Now, the key part here is that it is impossible. I'm not kidding, it's impossible to make sure the two things, database update and publish into the queue, happen simultaneously. Because you can always imagine the world where your application server dies just after it has written to the database, before the request hit the PubSub. If you send the requests in parallel, well, it can die somewhere in the middle, and you would never know which of these two succeeded. There are a couple ways to solve this problem. There are a couple ways to solve it practically, but not in theory. So they are good enough, but not perfect. And there are a couple good solutions in both theory and practice. One good solution in practice is to use what is called idempotency tokens. So this user who's creating the mutation request is probably using some client to make this request. Let's say it's a web client. So they go to tinyurl.com, they log in, they are authorized, they go to a certain page, which is effectively create new URL, and they type in the long URL, but optionally the short URL, and they click create the URL. What is usually done in practice, which is a really good idea, it's not a magic bullet, doesn't solve all the problems, but it's a really good idea. If you're not doing it, you should consider doing that today. When you load this page in the browser where the user can potentially begin creating URLs, you generate some random token, and you call it request ID. And you store it in the browser, in local storage, most likely, or in the cookies. So that if you refresh the page, you get the same request ID. And if somehow the user clicks shorten the URL, the browser sends the request to the backend along this line, along this connection. But somehow there's no answer, or it times out, or the error response is sent back. The client just sends the same request with the same request ID. And the beauty of this solution is that in the worst case scenario, let's say some load balancer service timed out. So it did send the request further. The application server has processed the request, but there's no confirmation back. So what would happen in this case? The application server would see the same request twice, or technically any number of times. The key part is more than once. If there's a request ID in this request, then you know for a fact it's the same request, and you can ignore the second, third, and whatnot. Of course, you would need to have a different request ID for the second URL shortener, for the second URL to shorten. But those are tiny details for the front-end developer, which most people these days know how to handle. So I'm not saying it's a perfect solution, but at least it makes sure that if there's a temporary short-term issue in the load balancer or in the network, the client can resend the same request, and the issue would not happen. I am surprised how many production services do not do this correctly. I keep telling the story all the time. It happens to me way more than once. I'm on my phone, I'm typing a comment on Facebook while I'm taking off on the plane, well, before I'm taking off on the plane. Then I click post, and I turn the phone off. When I land, I turn the phone on, I look into that comment section, and somehow my comment is posted there multiple times. Why did it happen? Because when I was taking off, the connection was already fairly poor. So at some point internally, some entity, could be my phone, could be some middle tier such as the load balancer, could be the application server, did the retransmission, most likely my phone. At least it was the source of this problem. So they made a retransmission, and somehow the Facebook's app does not have the idempotency token. And because it tried to post a comment multiple times, surprise, multiple comments eventually posted. Ugly, but real life. But this would not solve the second problem, which is how do you make sure that once the application server updates something in the database, simultaneously with this update of the database, the same update record is being put into the PubSub. It could be easy to do if the PubSub bus was part of the database, but to the best of my knowledge, there's no perfect solution for that. Now, you could use a database transaction. For the record, I'm covering the next 2 or 3 slides, which is just fine. We can just talk about this. So if your PubSub bus is, let's say, Kafka, it's a different request from your application server to the database and to Kafka. The database, if it's a well-built database, would have tons of mechanisms of its own to make sure that your mutation, your transaction, would either fully complete or fully fail. It would have its own request IDs, idempotency tokens, on the client side, likely. So the component of the application server that talks to the database, the binding that issues this update request, would have its own idempotency token. The database could have its own sharding, and the same request could hit multiple shards. Maybe there is a leader shard, and if it didn't reply on time, the request would be propagated to the other shard. We don't have to know this. We just need to know that the database by itself is doing its best to act at the black box, so that whatever is sent there is processed. So the real source of confusion is your application server might die between the moment it gets a confirmation from the database and the moment it sends the data to PubSub. In fact, between the moment it sends the request to the database and and successfully sends the mutation to PubSub. So this is actually, as I said before, this is a problem that cannot be solved. There are only semi-solutions. One good half solution is to publish in the PubSub beforehand, saying, I'm going to update certain key. And then once you update this key, you publish a second record, this key was updated. In this case, you make the logic on the client, in this case, the cache server, slightly more complicated, because whenever it sees a message, I'm trying to update something, it would have to set its own timer to maybe see if for this very key, the update did happen. The update did come through this PubSub bus within the next, let's say, 5 seconds. If it didn't, you're just looking at the database along this dotted line. That's not a perfect solution, because you can never have a guarantee that 5 seconds would be sufficient. But again, in practice, we don't solve unless you're building something super, super highly reliable, as in the nuclear plant controller or the world's currency.
From people who build something for nuclear plants, if you're using something like Postgres, I'm not sure about other databases, there is another possibility to connect this. So generally, all kinds of databases have their own transaction logs. Like for Postgres, there is a logical transaction log, which is available for logical replication. And anything that's committed to the database is also available for your application to parse from that. Generally, you can treat that as a kind of PubSub, which actually only publishes anything that's available in the database itself.
Yes, that's a very good point. 2 other solutions I have are exactly of this kind. I deliberately didn't want to talk about the bin log in this episode because it's educational. So let me jump straight to solution number 3, which is a canonical event sourcing solution. What you could do is you could emulate a PubSub within a database. We think of this database right now as the key value store, right? Short URL mapped to the destination. You could say I have 2 tables in my database. One is a key value store. The short URL is mapped to the destination URL and some index, which is the mutation ID. It's the index of this mutation in the whole existence of my service. So today I've shortened this long URL to the short URL, and this was the mutation at index 1,750 something. Once you update this, so in SQL terms, your mutation log, one step back. So you have your first table that maps keys to values. I add a new column, which is the index of this mutation. I have another table which lists mutations in the mutations order. So the key is the mutation index, and the value is the tuple, the cortege, the short URL and the destination. So technically, these 2 tables mirror one another. But the beauty of this is that they can be updated in the same transaction, in the same database transaction. So you don't really publish the PubSub yet. You may even want to skip the PubSub entirely. You can treat this database table as a PubSub. But what you ultimately do is you rely on the database's internal transaction guarantee that both tables will be updated simultaneously, or none would be updated. In SQL terms, for the second table, for the event log, you would have this auto-increment key. So you don't even need to do the magic yourself with incrementing the last modified, last seen, last updated index. You just have an auto-increment key table for the journal of mutations, and you have the actual key value store. In this case, your PubSub becomes secondary in terms of the data ownership. So what I've just outlined is the transactional event sourcing. It's a fairly standard technique when you want to have strict guarantees, and you know that the only thing you can rely on consistently is a database. In theory, it sounds like you would need to have twice as much data stored in a database. In practice, as I said before, this volume is minuscule. If it's 500 updates per second, it doesn't matter if it's 500 updates of one row or of 2 rows. But because you can rely on a database to give you this stamped index IDs, you can assume that your cache server, forget the PubSub. It's not even important if you have Kafka there or not. Kafka is just easier there for logical reasons, and interviewers like it. In practice, as long as your cache server or cache cluster knows up to which mutation index is it updated, it can just wait on new mutations, receive them from the database, and apply them to their respective memory locations. So I agree with you, Dorothea, that What you would absolutely do in practice, if it's a large-scale system, is you would have the means to subscribe to the database's transaction log, parse it, and treat that as a source of truth in the transactional sequential order. It would be a better design in practice compared to the PubSub I have here in between. Again, since we're talking how to reason about the systems and how to talk the same language with the interviewer, chances are if you draw the PubSub bus here and call it Kafka, it would be a better design. In practice, I think even if you do use Kafka there, and you will need to use Kafka there, if there's multiple data centers, multiple caches in different locations, you would still put Kafka there. It's just the way to update it would not go from the app server to the PubSub. It would go through another component somewhere here, which subscribes to the database bin log and updates the PubSub. So PubSub becomes secondary. The primary source of this sequential index stamped list of transactions mutations is the database's bin log. Was this clear? Because it's really important. Was this good enough?
Yeah, I guess it's important to highlight the thing that was new for me is that the cache server can actually have track the transaction ID to which it is updated. That's something that is often overlooked if you are using off-the-shelf solutions, which just don't have this concept.
Well, it's overlooked because Kafka was meant to replace it. Kafka started within LinkedIn as the means to replicate huge databases cross data center. So in a way, the fact that we don't talk about this bin log replication, manual bin log replication a lot, is the second order proof that Kafka is a wildly successful product. Because we are no longer thinking in terms of database mutation ID. We're thinking in terms of Kafka sequence ID, assuming that a certain Kafka topic contains all the transactions to be applied. And yes, it has tons of downsides because once you have multiple partitions, the order of messages is not guaranteed across those partitions of the topic. That's potentially really hard. But for the high-level overview, this should be good enough, I think. So this was maybe 2/3 of this slide. Now of the diagram. Now the remaining 1/3 is how do you shard the cache server? On this diagram, I've put the cache server separately from the mutation part, and I've deliberately drawn multiple cache databases there. That's actually a wrong picture. It's deliberately wrong. It's meant to invite for a conversation. In practice, there is an important decision to make. Do your cache servers act as totally independent entities? Or do the cache servers cluster? Does the cache server cluster, does their constellation act as one entity so that they operate in parts of the key space among themselves? For example, if you want the cache servers to be totally independent, which is a fine solution, I don't like it, but it's a fine solution. You could say, you know what, my actual cache, this database part, is Cassandra. Cassandra is a key value store, which is perfectly shardable. It can scale almost indefinitely as long as your actions pattern is single key, single value. So you can have as many cache servers as you need to handle the load from the read-only load balancer and from the PubSub. And you can have as many Cassandra nodes as you need to make sure the Cassandra database is not overloaded. That is a fine solution. But you have to understand that if you do it this way, you would rely internally on Cassandra's means to shard the key space across its own nodes. So we will not go deeply into consistent hashing right now, but the way Cassandra works and the way most NoSQL databases work is Dynamo works the same way too. You can always add more machines to improve capacity and latency, because more machines get the load distributed evenly along them. If you add machines, if you had 10 machines and add another 11th machine, the way the key allocation across machines would happen is it would take 10% of each of these 10 machines approximately, take it to this machine, and it would evenly redistribute the key space across now 11 machines, which means you can use more RAM, more disk, and enjoy more throughput and low latency, and vice versa. You need to make a decision. Are you relying on this underlying key value store such as Cassandra to do this sharding for you? Or do you do it yourself so that you can tightly couple your cache servers to the cache database shards? So the design that is traditionally canonical here would be what I just outlined here. You would say, well, I shouldn't call it canonical. The design that you could present on an interview and you'll be just fine is that, hey, I'm going to use Cassandra here because it can scale indefinitely. In this regard, every cache server is totally independent. They're all identical. If my cache servers are overloaded because there are too many requests from here, from these guys and gals, then I just add cache servers, and if my database is overloaded, I just add Cassandra nodes. In the real life, a better design would be you don't use Cassandra, you have your own cache server tightly coupled with a consistent hash and ring with your log system so that it carefully knows, so that the nodes will know exactly what to update in their own respective caches, and you'll probably have the data duplication factor of 2 or 3, so that if one cache server dies, it's some other cache server has all the data this cache server has, all other cache servers collectively have the copy of the data this cache server had, so there's zero downtime. Not saying it's the best solution, it's just slightly cleaner if it's a large-scale design by yourself. But for an interview, you don't have to talk about this at all. Just mention that you understand these things, understand the bottlenecks. Any questions so far?
Probably a comment. So for when you're keeping the cache server consistent, you can probably, like, one way to treat it is also connected with the question whether to push the very first, whether to push the link once it was created or once it was clicked for the very first time into the cache. The one thing that you can do is to just remove the entities from the cache and keep treat the 404s and not found as proxy to the database and have a lookup in the database. In that case, you don't have to actually track anything in cache except for invalidation.
True. Yeah. You can get rid of the PubSub entirety as long as you. So in this diagram, there's a dashed line between the cache server and the database. So the cache server knows they can go to the database, but they're not expected to do it frequently. You can always say, ignore the PubSub, just assume the cache server can go to the database to get the update. Here's what's hard here's the bad thing about this design. It's actually a really important point. Consider an extremely simple attack on your service. I'm going to keep trying to resolve the URLs that don't exist. I can easily generate millions of requests per second to your service, which would just try to resolve a random short URL. Most of them would not exist. In order to figure out that they don't exist, for 100% of those requests, or close to 100%, the cache server would have to go to the database to just get a no answer, which is a terrible flaw in such a design because it would work in a happy path. It would be too easy to bring down. So at the very least, you would need to have some kind of a Bloom filter on the cache server level to have a quick rejection test. Hey, I know this URL doesn't exist there. And once you have the Bloom filter or whatnot, at some point you can try to click on a URL that doesn't exist, and then a second later it's there, unless you push this update to the cache server from the app server. This particular cache server would sincerely believe the short URL doesn't exist. See, I really love this problem because it sounds simple, but it opens so many doors.
Can I ask one more question? Where on this schema is the guy who is tracking all the statistics? Because you said before that with every click we need to log. Who asked for this information? And we don't just ask cache server for that. We also need to store it somewhere.
That's a good question. It's not displayed here. The easiest solution I can think of, again, the way I think about this and the way I encourage everybody to think about this is, do we have the data points, the source of truth for each event? Can you rank them in like a DAG, directed acyclic graph? So from A follows B, from B follows C, but never back. In this case, what I would say is, well, yes, every single read, every single request goes through this load balancer, to the cache server. I'm going to put a PubSub somewhere here. A huge PubSub could be a Kafka cluster because the order of clicks is not important. And for every single click, I'm going to publish a message there saying, hey, I had a click from this IP address on this link. That's it. The rest, a different service can handle, which would look a lot like this one, except it's internal, so there's no external load balancers. And yes, I sincerely believe the statistics aggregation and the statistics reporting part, back plus front, would require at least 10 times more machines than this part of the system. That's why I keep saying that interview grade system design is very different from real life system design. But
and another note that ClickHouse was built for this, and it was specifically designed so that number of machines would be minimized. So even though if you build it traditionally with some other means, you will have to have a lot more machines. With ClickHouse, you probably need just a very similar amount.
It's another kind of worms. I'm also changing in my perception of this problem space. 10 years ago, I would say it's a waste of machines. Like somebody could tell me, hey, I could put Elasticsearch here, and that's all I need. And I would say, why so? You would waste so many machines. These days, I'm pretty much converted to another camp. Machines' time is a lot cheaper than developers' time, and most products by most companies, you can't really predict how wildly will they grow. So if you design every system, assuming that it's going to grow by a factor of 1 million, nothing would ever get built. So it's only healthy that we actually teach people how to build systems in the way that is just using standard blocks in the correct combinations, even though it's perfectly inefficient. Because if it's like a 10x machines or 10x RAM or 10x CPU, it's a constant factor. It's like in the computer science algorithms theory. If you have a 10x worse algorithm, it's a constant factor worse algorithm. What you care about is changing from n squared to n log n. You don't really care about going from n squared to 1/10 of n squared. So yes, you could use ClickHouse here, and it's actually a perfect fit for this particular problem. Again, if it's my own system, well, first of all, if it's my own system, I probably wouldn't be designing this part. It's kind of straightforward. But if it's my own system and somebody tells me I'm going to do it this way, 5 years ago, 10 years ago, I would object relentlessly. I would argue it's not the best use of CPU and whatever. Today, I would say, hey, it's a good idea. It's going to work. It's going to work predictably. It's going to be maintainable by people who just know how to use the standard components. It's scalable. And it's scalable in the sense that you can always, if you suddenly start growing exponentially, you can always throw money at it, and it scales, as opposed to having rebuilt the whole system. So, and I sincerely believe that as of today, if your goal is to convince some team you would like to join that you are a reasonable person who knows how to build these things, you're better off starting from this and then finding your way up, explaining more advanced topics, assuming you're comfortable talking about those and the people you're speaking with are also at this level of comprehension. Make sense? All right, let's see how many slides did I actually cover. Life of a query, how does it work with consistent hashing and list recently used? Covered. So failure modes, covered. We talked about the actual failure mode of the application server being enabled to simultaneously guarantee that it updates the database and the PubSub bus, and we talked about how to work around this. You can do event sourcing, you can do it on the database level, you can have an extra event published, and you can design for replayability. I do want to point out that PubSubs are important. In fact, if you care about making sure that, let me go back to the diagram. So there's a PubSub here. Again, could be emulated in the database, could be bin log of the database, doesn't matter. There's a PubSub here. I argued in the later slides that you might need a PubSub here between this load balancer and this application server, because if the application server dies, you probably don't want to lose these requests. It's kind of optional. I don't think it's as important as this guy. For this guy, we covered why is it super critical. Because if you don't have it, we have this issue of potential attack of empty URLs that don't exist, and then suddenly you update this URL and it's still not up to date. It's important here, but not here. So I don't think you need a PubSub here, but if you would like to argue that it's useful there, if I'm the interviewer, I would not object. As long as you can explain why, and it's not hard to explain why, I would totally accept this solution. Yes, and we talked about emulating behavior, the behavior of PubSub with the database. What did we not cover? Kinda intentionally, because I tried to make it an under 1 hour episode and I think I failed already. So the database is supposed to just be there, which is not always the case. I mean, it could be a cloud database, which in this case is always there. But in practice, if you're a mid-sized service that is refusing to use a cloud database because of costs or vendor lock-in or whatnot, you probably would need to hire some DBAs who would configure the database for you, which kind of is always there. Just keep in mind that it would be far more than a single box. It would be a distributed system with its own leader elections, with its own recovery modes, with its own failovers, potentially pages to your DBAs, etc., etc. The PubSub is also supposed to just be there in the design I presented. Again, Kafka, if you use Kafka, Rabbit would do the same thing. You would need to configure it. You would need to put multiple machines. You would need to replicate the data so that if any one machine dies, your data is not lost and it's still replayable. Note on cloud primitives. Well, first of all, I mentioned Cassandra before as the potential backend for the cache database, in-memory database. Well, you could use Dynamo there if you're on Amazon, but then keep in mind that if you're suggesting the solution during an interview, the immediate question you would get would be, so you have Dynamo as a source of truth, right? So why not just use Dynamo? Why do you need a database at all? Which would be a correct argument. So if you do use Dynamo, by all means, you can use it as a source of truth. This system, this problem, as I mentioned before, is effectively about building a large-scale key-value store, and Dynamo started as a surprise, large-scale key-value store. So it would just do the job. The way I view this dichotomy is very simple. Even if you want to rely on cloud primitives, you have to understand how they work internally, because at some point, it just becomes about cost optimization. If it's a cloud system and you're using it in the way it's intended to be used, chances are it would be easier and even cheaper to run it on the cloud. If you want to use something unconventional, there's a good chance that the price difference between having your own optimized system, because it would combine storage, compute, and the PubSub capabilities, this system you build by yourself could easily run at 1/10 of the cost of using a cloud primitive, because you would use this cloud primitive in a non-standard. I mean, you would have to use it in standard ways, whereas your program is not standard. So again, as I said before, as long as you don't care about money, and oftentimes you actually don't care about money in these cases, by all means, if you're cloud first, cloud friendly, use a cloud primitive. Just, I urge you all to be aware of how these primitives work behind the scenes. Second half. We didn't talk about how do we shard the application servers. Well, we kind of did. They're all fully independent, so it can just be multiple machines behind the same load balancer, and the load balancer does some round robin across those, and that's it. We didn't talk about how to shard the cache servers. Well, again, we kind of did. There are two religions here. If you can design for cache servers being totally identical, totally fungible. If one dies, it's okay, or you can replace it. In this case, you would need to shard the cache database. You have to pick the cache database that is infinitely scalable and shardable, such as Cassandra. Or you can combine the two, so that you would effectively be re-implementing parts of this Cassandra logic, which is consistent hashing, green and stuff. You would need your own log system on top of you, like ZooKeeper or console or etcd. But you probably can achieve the same result using fewer machines. For production designs, if it's a high-loaded system, I would recommend the latter approach, do it yourself. For the interview, I would totally recommend the former approach, because it works. Even though it's suboptimal, it's easy to reason, and it's a good starting point for you to clearly demonstrate you understand how these primitives do their job together. So yeah, this one we also covered. that look at the second half of this. We can have the database schema extended from just one key value table to update index into this cortege of these two elements. And then at this point, oh, actually, there's a bigger point to be made here. We did cover that you could build this replayable event source log within a database. What we did not cover is that once you go there, nothing prevents you from going all in and saying, I don't care about the key value store. I care about the mutations log. Which is perfectly fine, actually, because, yes, if you would like to look up for the... Imagine that your database is Postgres. If you would like to look, if you don't store the key value mapping, if you only store the mutations log, and you need to write a select query, they would tell you what is the current destination of a certain short URL. Well, you would have to select all mutations of this URL, order by mutation index, pick in a descending order, limit one. So pick the latest update. Certainly, it's far from effective. But you never run this query against a SQL database. You always run this query against the cache. So then that's what the cache is for. So you can actually design the system so that the source of truth is not the database as in key values, but the database as in the mutations log. In fact, I would actually recommend this design highly. But again, if we're talking about simple interview, don't talk about this until you know exactly what you're talking about. If you know what you're talking about, do talk about this. I think it's a better design. Yeah.
I have a question here.
Sorry?
Yeah, what if how then we handle cases where when non-hot URL is being accessed a couple of months later? Sure, it's not in the cache, so you will have to query this log to find out the value.
Yeah. Well, you wouldn't query. Oh, I see. Good point. So yes, if you do go all in on the mutation log as a source of truth, then you would need to keep the key value mapping of that on the cache node, not just on the hot cache in memory, but also on disk.
Okay, yeah. So we still keep it, but we just presume that this is kind of a cold cache.
Yes. So yeah, if I would design the system today, what I would recommend is mutations log as a source of truth, my own cache nodes with consistently hashed string so that it picks the right cache node in a consistent fashion. And it's actually even unnecessary, but it doesn't matter. And every single cache node would use all its RAM for least recently used cache and all the URLs in its disk, because disks are super cheap. So actually, yeah, forget consistent hashing. I could just load balance round robin against over all the cache nodes. I would make sure all the cache nodes are identical. They store all the mappings on disk, and they keep the recently used cache in memory. And that's all you would ever need. The only pragmatic use case here would be if you need to start a new node, a new cache node. You don't want to replay the log from the very beginning. You would have some snapshot. But you can take snapshots of your cache nodes, let's say every midnight or every Saturday night, and that's all you need.
Well, after you gave this explanation, it actually goes that, well, if you go with Postgres, which is familiar for me, we just have a writable master and we have multiple read slaves. And instead of what you present as cache infrastructure, we just use read slaves, which are gonna manage that using their own system primitives, already existing ones, because you already have the cache, you already have actually even your all of the primitives that you are showing here are actually present in Postgres, even if you use the very basic update, insert kind of SQL.
I'm aware of this. And that's another huge difference between real-life design and interview-style design. If you suggest this design to an average interviewer who doesn't know much about Postgres, you would have a hard time explaining that it's a good design, and your explanation would have to pretty much cover everything we just covered. So in practice, I'm 100% with you. if your database of choice is Postgres and you're familiar with it, and you are, certainly you are, I see literally no downsides with Postgres first design of both the application servers that do the mutations and the cache nodes that do the reads. You can just put Postgres everywhere. It would still have to be multi-leader setup on the application server side because you need to support high availability. You need to have some leader elections here. But assuming you can handle this, yes, you can just use standard database as hot plus cold cache and add as many nodes as you want. Oh, one thing you would have to worry about is if you replicate from one database to 100 machines, you don't want to have 100 pipes going out. You need to have some multiplexing, right? One machine goes to one data stream goes to 2 places to go to 4, etc. You don't just go 1 to 100. You saturate the network and CPU. I'm not sure if Postgres can do this. Andrei?
Yeah, it's outside actually of responsibility of Postgres. Like the way that the log is moved between machines is outside of its responsibility. So there's multiple solutions that actually handle this, including in the more complex schemas.
Yeah.
But I would split still anyway. So the idea that Dima presents in terms of architecture as a cache, the backend databases like the Postgres is there might be even some real life use cases where it might not be applicable. I might be wrong, but I would see this cache, some functionality for this cache as must-have as actually time-based lifetime. So for instance, I mean, if we talk obvious again, Redis thingy. So you just set up in such a way that you don't think about how long stuff is in Redis. So you just put the upper time limit, and then your code or your architecture works the way that, okay, it's not there, then be aware that it will take longer to verify for me as a system that this URL exists or not exists. But if it's there, you get it straightforward, just straight away. So kind of that thing.
I'm honestly, it's a very good point, but I'm honestly divided in my thinking right now because that's exactly the moral dilemma I'm having. I'm trying to talk more about how to design real systems, but I'm also trying to give some intro to how to pass interviews at this point. So so I'll try to speak up about the common denominator. The common denominator is the following: the better you can reason about how to use the standard primitives with pretty much no custom code, the more resilient your design would be. In the design that we just discussed with Postgres, you're right, Dorothy. You would need to design this one-to-many replication by means of some tools that are outside the native Postgres installation, which means that in order to support this system, you'll need to have experts not just in Postgres, but also in how to configure and maintain and troubleshoot these components. I'm also a Postgres fan, but in this particular case, I would go with Antonio and say Kafka is the best solution here, because it's a lot easier to find Kafka experts, and it's a lot easier to find people who would tell you before something goes wrong, hey, looks like your Kafka partition is misbehaving because something is wrong with its CPU utilization or disk use. Whereas in your solution with Postgres, unless you have some full-time people monitoring this, it would suddenly misfire at the worst possible time for you, and you would not know how to fix it overnight. So it's always a trade-off.
Yeah, I guess the thing is that the diagram that you had before for the whole system, like you don't really put the names of the components, and the off-the-shelf components like Postgres or Kafka or some other things can actually be used in multiple roles. Like as you mentioned, for like it doesn't have to be always Nginx or always Redis or always something like that as a cache, because your operating system already has a cache layer for disk or some other cache layers, and you actually need to use some of the off-the-shelf blocks to run as a cache. rather than take something that has a cache in its marketing description.
Well, yes, that's actually, while you were saying this, I realized my brain is fully transformed to this educator mentor mode, because I deliberately did not put any names on the diagram, even though when I was talking about this, I used the words SQL, Postgres, Kafka, Cassandra, and Nginx, which I think is, I'm not sure if it's the best way to do it, but it's just the way I've converged to thinking. When you draw a diagram, it's primarily to help you explain your thoughts. And I think I'm totally with you. Your cache could be a file system with a ZFS, a single directory with all the URLs and files. It would work in many cases, but logically it's still the key value store on a cache machine. Same goes with load balancers. I actually meant elastic load balancers of Amazon, that can round robin automatically for you. But sometimes if you want to add headers, you would have to put engine access there. But to me, those are far below the level of system design that is worth being called system design. Those are implementation specs, much like your API endpoints. How do you name them, or how do you parse numbers or strings? I think my job here, my goal here, is to make all of us a bit better at reasoning about the components and how they talk to one another, and how to use standard components, and how to not use standard components, which is also important. Great questions, thank you. I got a few more things to say, just a few, promise. So yeah, on PubSub, the point here is ideally you prefer push over pull, because pull can be slow and time consuming, and it loads CPU and needs more machines, etc. At the same time, if you have a batch job, pull is perfectly fine. In fact, for batch jobs, pull is better. It's much better to say, hey, I'm going to schedule this batch cleanup or batch audit job once I have the CPU resources for that, as opposed to I'm going to set timer for this to happen 1 hour from now, and then suddenly 1 hour from now you are at peak time. If you don't have the PubSub in our original diagram, if you don't have a PubSub bus between application servers and cache servers, you can still pull the database. You can always query the database, hey, what's the latest mutation index? And then if this latest mutation index is ahead of my latest mutation index, I need to get this data and get myself up to the latest index. Perfectly fine. If you make this request every second, you probably are still in a good enough shape. Just keep in mind that if you have to go with this design, if you cannot do a PubSub, if you have to pull, don't pull the very database from every single machine. You can have this database replica as RFA suggested and talk to this local replica. If you had like a cache cluster of 20 machines, put a database replica there and talk to this replica. If you have a cache cluster of 200 machines, you can put 3 replicas here. The point is, these replicas can be synchronized with the main database every second or whatnot. But every second or whatnot, all these cache servers can talk to these replicas as opposed to the main database. That's an extremely important point. Every single time you can distribute the load by putting a local proxy, local cache, at least mention this. It actually helps in the long run. Cross data center comments. So my diagram was explicitly a single data center. Usually you would want to design this kind of things in a cross data center fashion, at the very least for data consistency. So when it comes to data reliability, I always said that if it's a single database entity, in practice it's still multiple machines with a leader and active cluster. So if one of the machines explodes, the other ones keep the data. Tiny detail, you probably want to configure these database machines to be on different racks, if not on different availability zones or power supplies. It's actually okay if your mutation takes more than 1 millisecond, let's say 5 milliseconds, as long as you keep your throughput guarantees. The fact that your machines are further away from each other physically makes your data more secure. The fact that your data has to live in multiple data centers makes this data even more secure. Now, not only are you protected from a single machine exploding, you're protected from a data center being destroyed by an atomic nuclear explosion. So fundamentally, in terms of perfect solutions, like stable, resilient solutions, do distribute the data across data centers if you can afford to. In this particular case, the cross-DC part is actually not too hard. You would absolutely have cache servers duplicated in every single data center. I think it makes perfect sense. If the user from Australia is trying to access a short URL, they go to the Australian cluster. If the user from China would like to access short URL, they go to their local data center, and etc. etc. The trick is that the database that you use for mutations and the source of truth, be they the event source records with version mutation indexes, or be it the PubSub bus, this part you would have to be careful with, because you cannot put it into every single data center. You need to synchronize the databases. It's a complicated conversation. We don't have time for it right now. But the trick is, I think, the biggest takeaway is don't dilute the data authority. It's far better to have a design where at any point of time, only one data center has the authority to make mutations to the database. This one data center can be moving. Like you can change it multiple times a day to be in a data center where the most traffic is coming from. But in our particular problem of URL shortening, if suddenly you're in Australia and the leader data center is in the UK, fine. Extra 150 milliseconds of time it takes to create a short URL. No big deal. You can live with that. So if you really want to make it even faster, then you would have to design Spanner with its own synchronized. So the point I'm making is either you have a single machine, single CPU core of a single machine, through which all the mutations go, because only this particular entity can order them in time, so that if there's a conflict, this entity resolves who came first. Either you have this one machine that does it. It's of course leader elected, so if it dies, the other machine takes over. But either you have this one machine that at any point in time, at any point of time, it's guaranteed to be the entity that resolves conflicts, or you have to invent Spanner in a sense that you have to have super synchronized clocks across data centers, which, to the best of my understanding, not many big companies have done successfully. So if you do need to support 100 updates per second with high latency, like in a TinyURL case, no one cares. If you need to scale this, let's say by a factor of 1000, so you suddenly have 300k QPS per second, but your URLs are all independent, you can just partition the key space and still use the same solution. If you need to support 300k or more QPS, and you have cross-key dependencies, which you need to resolve atomically, well, this problem suddenly becomes next to impossible to solve in a generic fashion, and you have to think about which trade-offs can you make on the problem statement level for this problem to become solvable. That's a totally different conversation. I'm eventually going to have it with, I guess, some or all of you, but let's not do it today. Just the takeaway here is don't try to solve the hard problems. Cap theorem is impossible to overtake. Data authority, if it's distributed, is impossible to do correctly unless you have a single leader that is responsible for making these changes, or you have a really synchronized atomic clock, which is Spanner, and honestly nothing beyond Spanner today. I mean, when I say synchronized, you can design a system so that the clocks are semi-synchronized. Let's say use an NTP, you get like sub-second guarantees, not milliseconds, but sub-seconds, in which case you can still order transactions that are more than a second apart. But if you want it to be sub-millisecond thingies, well, Spanner has like 7 milliseconds guarantee of no time skew. But if you want it to be multiple times per second, real-time updates, cross-dependency between multiple keys, so the same transaction would span multiple keys, and these transactions would happen in multiple data centers simultaneously, don't even try to solve it. It's nearly impossible. That's the gist. This is a slide I had to make. Again, it's my bias. I view all these database problems, all these updates as exactly once delivery problems. If only we could have PubSubs that guarantee that once the message is there, it is there forever, it's replayable, and it has a fixed order from 1 to n. If only you could have these PubSubs reliably, we would have no problems at all. We could just rely on them. We would just have everything as a materialized view, and these PubSubs would be the source of truth. Unfortunately, it's not possible, even with Kafka, that does not have this guarantee of order of messages if the topic is partitioned. And within within one topic, one partition, Kafka only gives you like 700k messages per second, which I think is remarkably small for any large-scale system. But it's just my personal view. I should mention that there are new SQL solutions, such as Single Store, formerly MemSQL, such as Gigabyte. So people are building databases that have these guarantees taken care of. I do think they will earn their place soon, but I haven't used them in production myself. I'm not entirely positive they're production ready today. I mean, MemSQL must be, but it's probably expensive too. So yeah, the takeaway here is that if you're dealing with a problem of this magnitude and this complexity, chances are using Spanner or Dynamite, paying Google or Amazon for them would be a good idea. Where are the final few slides? So again, my goal here is to make sure we can all reason about the standard primitives and how to use them correctly. And to use them correctly, it's important to understand which superpowers do they give us, so that we use the superpowers, which we would otherwise have a lot of trouble implementing ourselves. So we use exactly once guarantee. Fundamentally, that's a big insight, by the way. It's hard to explain within a few minutes. But fundamentally, we talked about using a PubSub bus as the means to deliver updates from the application servers to the caches. Or you could use the database stored event mutation log, event sourcing technique, to order these events and replay them in the order. Fundamentally, both tricks use the same meta trick. They make sure that you have the exactly once guarantee on how to replay the updates. Either this exactly once guarantee is given to you by a Kafka stream, or is given to you by a database transactions engine with auto-increment index fields. The point is, you would not be able to do it yourself unless you try really hard. And there are at least two solutions that give you the same functionality out of the box. One of them is database transactions, and the other one is replayable PubSub such as Kafka. If you want to do it right, we will not go deeper right now. But if you want to do it right, this would involve leader elections. This would involve console, ZooKeeper, Paxos, Raft. Paxos and Raft are impossible to understand. Kafka used to rely on Raft, I think, right, Antonio? Now they have their own leader elections mechanism these days, so it's slightly easier to deploy.
Yeah. Now Kafka does not need ZooKeeper, so ZooKeeper has its own consensus protocol. Now Kafka, I believe it uses Raft, if I'm not mistaken. I'm not quite sure.
I think I'm a good engineer, but I would not try to implement Raft today on my own, because it sounds simple on the first try, but once you start thinking about all these possible disconnects, message packet drops, if your network is partially down in one direction between certain parts of the cluster you're working with, it is really hard. Don't do it. So yeah, my recommendation here is use something standard, which hides this complexity and gives you just the guarantee you need, which in this case would be either RDBMS grade transactions or Kafka level PubSub delivery and ordering and replayability guarantees. The minor superpower we used is consistent hashing. Again, not much time to talk about it right now, but basically when we mentioned using Cassandra as the backend, as the provider for the cache database that scales infinitely. You are using Cassandra internally. You are using consistent hashing internally. You are using the technique that allows you to add more machines to grow your capacity and lower latency. Again, this is something I could implement overnight, but it's not something I would recommend you guys implement. What we did not do, which is also highly important, we did not design distributed transactions. So it's a common mistake. It's a huge mistake in an interview, but it's also a huge mistake in the real life. Remember I mentioned that it's impossible to make sure your application server would update the database and simultaneously update the PubSub. It's impossible. It's impossible because you never know which part of the system fails at which time. And even if you hedge yourself against every one part of the system failing, I'm almost positive I can come up with the failure scenario where something is sent, then dead, and then received, but before it sends the acknowledgement, it's dead again, so something will be retransmitted on the TCP level. So in order to reason about all this correctly, trust me, you do not want to do it yourself. So in practice, when you want to design the solution for this in the industry is called two-phase commits, when you have to do it yourself, when you have to have this guarantee implemented in a software of your own code. You'll need to renew two-phase commits. I should add the link here. I will. If you're designing two-phase commits, you are doing something wrong, I think, unless you can avoid the pain of designing a two-phase commit by putting everything into, yes, replayable Kafka streams. So my intuition here is no two-phase commits manually, perfect world. use database transactions and Kafka streams and whatnot. If you need to implement two-phase commits manually, at least make sure you don't have circular data dependencies. So make sure that from A follows B, from B follows C, and between every pair of components there is a bus that is replayable. That's a simple heuristic to make sure you would never ever end up in a weird deadlock, in a weird situation where the data is inconsistent. And if you do need to design a system like this, do look into CQRS. I think it's the paradigm that is more than 10 years old, but it's still, I think, the best solution for this kind of problems. It's the best concept to combine event processing, event sourcing, plus event sourcing with application level APIs that the users are facing. We did not have single points of failure. We talked about this. We tried to avoid databases polling, and we did not try to cheat the cap theorem. We always were very aware that we are eventually consistent with respect to potentially serving stale data, but not being unavailable if some connections are broken. That's it.
Yay!
I have a question too, actually.
Start with the first.
Actually, I'm going to start by the second because I believe it's faster.
Antonio, do you mind if I scroll back to the slide with the diagram? I think it's a better one to look at.
Yeah, I have one question about there, and one is actually 2 slides before this one. If you could just quickly go, no, the next one, 28. Okay, what by consistent hashing is coupled with a log service? Just so I understand it, I got it right. Do you mean like, okay, I'm a node and I can take some regions from the ring, what is available, and I check this log service? Is that the logic that is meant here?
Let me try to answer this within a few minutes because it's already a tricky, deep question. So the consistent hashing is a technique to split the key space across machines in certain fashion. This fashion gives you a nice guarantee that if a machine dies or is added, the reshuffling is minimized. But the superpower is not in this. The superpower is that in order to make this work, these nodes don't even talk to one another at all. These nodes just need to receive updates from some log service authority, which will tell them which of these nodes are currently available. That's it. I guess the message in the chat is Juliet taken off. Thank you.
Okay. Yeah. Yeah, makes sense.
So yeah, the way you would, if it's a few machines and they can all talk to each other, you can probably have them leader elect the leader that would shard the key space across them. If you need to consistently hash the huge key space across, let's say, 1,000 machines, it's just infeasible for them to talk to one another. So what you would do instead, you would have the log service. I used to call it log file system. I think log service is a better term these days. So you have ZooKeeper or console or whatnot. And this log service acts as the small database that is small replayable database, actually. It's a trigger to describe what it is. But what it does is it stores the consistent state of the fleet observed identically by all these components. And all you need is for these components to all see the identical state so that they don't talk to one another. And the load balancer that would send the keys to this cluster also doesn't need to talk to any of these machines. It observes the same state of what is active. It computes the same mathematical function. It knows exactly to which shard to send the message.
Yeah, makes sense. I was thinking more of approach of a core algorithm. I believe that's the name, where you store some of the machines, and it may go exponential, and the runtime, I believe, will be logarithmic for accessing some region. Anyway, thank you.
I'm not too familiar with this, but I think so. I'm not familiar with this at all. But the trick is, I think in practice, the solution that would use leader election such as Raft as part of this log system, and then consistent hashing that distributes the key space across multiple machines, as orchestrated by this log service, I think the solution will be superior because it's possible to optimize it with no logs whatsoever.
Yeah, but in that case, we're introducing another service here to the system, right? The logs system. Again, I'm not advocating for the solution that I'm proposing. I'm just saying that there's two, and it comes with a trade-off.
I have an idea. I have an idea. We'll talk about this off the record, likely not today. And I think in this educational series, consistent hashing itself deserves a dedicated episode, which would be, I think, one of the next ones.
Seems good. Yeah, sorry for turning this out.
So for your other question, you wanted the diagram, right?
Yeah. I believe it's slide 17, if I'm not mistaken. And you mentioned that between read write and the app server, one solution to cope with the app server failing would be to add a PubSub between the load balancers and the application. But in that, if I got that right, in that case, wouldn't we move the failure tolerance that we want to introduce? We just move that failure to the PubSub, right? We wouldn't solve any problem, because from the beginning, it is clear that read write is consistency over availability, whereas read only is availability over consistency. If I got the assumptions right at the beginning. So in my case, and you mentioned that it is possible to defend that PubSub here would be, it would be a valid solution, but I'm not just picturing an example or reasons for it.
Oh, it's because I didn't phrase it well. I think I can answer this. So there are two things. One is there are two things I didn't phrase well. One I didn't phrase at all. One I didn't phrase well. The one I didn't phrase well is the consistency part. We do prefer availability over consistency, but that's on the serving side, on the cache server side. In practice, what you want is super high uptime on the actual serving, but your uptime requirements for the creation of new URLs or deletion or updates can be a lot lower. So if every single day there is a 10 minutes interval where you cannot create new URLs and the system tells you server down, come back later, it's really no big deal, more or less. So the term consistency has to be used carefully across these two universes. They're not identical. And to your main question, if you put a PubSub, if you put a Kafka between the read-write load balancer and the application server, the beauty of this solution would be that Kafka supports, you know this better than I think most of us here. With Kafka, you can prefetch the entry, but until you have acknowledged, you have processed it, it's going to be sent to a different subscriber eventually. So the trick is, if your application server dies in the middle of processing some request to create a new URL, what you want to have is a different application server starting up and actually serving the same request. If you put Kafka here between the read-write load balancer and the application servers, then it doesn't matter if the application server died while serving my request, because my request still lives in the Kafka PubSub. So the source of truth for this request is in Kafka. In practice, you could emulate part of this logic on the browser level, as I said before. But then again, if you click create short URL and your computer dies, your battery dies of your laptop, you cannot be sure that it's successful. If there's a Kafka there, then once the message is accepted by Kafka, the load balancer can already say, I confirm the receipt of your request. Here's your Kafka stream ID or whatnot. You can pull on this request ID, and it's being processed, and it's guaranteed to be processed eventually, even if it takes a few hours because we are in a huge outage.
Yeah, you're measuring consumer groups and the commits and so on. But on the read-write, and that's the load balancer, I believe, at least in Amazon, if I'm not mistaken, load balancer is able to replay the messages. So I would expect if the messages they do not receive an acknowledgement, like the status 200, you could later on replay those messages.
I'm not aware of that. might be true. I have
Yeah,
not. I have not done it
think
before.
Yeah, because I believe I don't remember the whole architecture, but we did it once.
You would have to configure this manually, I believe, because if it's not the case, I'm almost positive from first principles that you would have to configure this manually because if it's enabled by default, some poor developers would struggle because they would have double processed requests if some of their servers, if the application server does process the request but forgets to send a response or dies, they would somehow get double processed requests when they don't expect this to happen. So I would, since Amazon is so user-friendly, as in they are trying to make it harder for the developers to shoot themselves into the foot, I'm almost positive it's not enabled by default.
Yeah, I don't think it's enabled by default. Otherwise, it would enable like thundering hertz, like your application just crashed and now you'll face a DOS by the load balancers.
But then look, if it's possible, then effectively this feature of the load balancer would effectively be that Kafka stream between it, inside it.
Yeah,
so so from the system design perspective, as long as you can argue that, hey, I'm going to put this checkbox, enable this method of the load balancer, that's effectively as good as arguing that you put a Kafka stream there, even better because it's managed by the cloud provider.
Yeah.
I mean, in this case, you would have to mention that it's Amazon specific and you don't know about Google and Microsoft and Azure, in which case, as I always say, unless you absolutely have to, don't lock yourself to a particular vendor. So yeah, all good questions, all good conversations.
Yeah, I believe the idea would be some sort of discussion that as it was happening just now between the two of us. Like, okay, I would put a PubSub, but if in the load balancer, like the cloud providers have this option, then we'd have one less thing to maintain. And that's good. That's a win for everyone. Anyway, thank you. Those two were my questions.
Thanks, Antonio. Good questions. Thank you. Maxim?
No questions. Thank you.
Thank you. I think it was pretty good, even though it absolutely took longer than I planned, which kind of was expected. But I think we did cover quite a bit.
Yeah, we did.
Thank you, guys.
And I really, we can discuss offline. Yeah, after.
Yeah. Let's call it for now. Thanks, everyone.